Zach Stone here. This is our fifth and final video of our Ohm Guru's continuing education seminar on power flow transfer between two buses. In this video, we're going to pick up exactly where we left off. I'm going to share with you a real-time phasor diagram model that I built that lets us see just exactly how all of these variables interact with each other in real time. We're going to change the torque angle and the real component of the sending voltage, making them both bigger and smaller, to see exactly the effects they have on things such as real power flow, reactive power flow, power factor, current, voltage drop, and more. This is an incredible model that really helps to put together the bigger picture of power flow. If you haven't watched the previous parts of this video, you may want to pause here and start there instead. And if you're studying for the P exam, this is going to be an extremely helpful video for you because, as you know, power flow is a subject on the exam. If you'd like to learn more about our continuing education seminars for professional engineers, come check us out at www.ohmgurus.com. Does all this make sense? Do you understand why I wanted to take the time to derive those equations first? Do you understand why the real power receiving, just shown as P here, will always be equal to the real sending power when the resistance is equal to 0? But do you see how the complex sending power does not equal the complex receiving power, and the reactive sending power does not equal the receiving reactive power? Does everyone see that? Can you understand it with the math? We solve those formulas using VR. We didn't solve those formulas using VS. We're looking at VR as a reference. How much power is actually making it into that bus, minus any losses? And then the polarity of VR, again, is it positive? Is it absorbing that power like a load, whether it's real or reactive? Or is it negative? Is it actually sending that power? Good. John said, yes, knowing why is just as important as knowing that. Yeah, I agree. The first time I learned this stuff years ago, I was pulling my hair out because it's like everyone had a different, there's only one, you only ever see one formula for real power transfer. Why? Resistance is equal to 0. No real power is absorbed in the line. So whether you're looking in terms of the sending bus or the receiving bus, it's the same value, same formula. But I guarantee you after the seminar, if you want to have some fun, go ahead. I challenge you. Google the formula for reactive power transfer. You're going to find 3 different formulas, all called the same thing. You're going to get the receiving reactive power formula that we derived today. You're going to get the sending reactive power, and you're going to get the power absorbed in the line. But they're all going to call it the reactive power transfer or the reactive power flow. People don't get it. It's nuanced. These are different quantities because of those line losses. But now you know the difference because we took the time to derive it. All right. So check this out. Look at this. Ready? Here's our diagram. Can everyone see the phasor diagram model? And there's about 95, 96% of you submitted the quiz. Go ahead, submit the quiz now because I want to launch the instructor eval. I know some of you have to drop off. So go ahead, submit it now before I close it. So look at this. Here's our sending bus. Here's our receiving bus. VX, this black phasor, that's just a voltage drop across the two of them. Current is always going to flow in the direction of real power. And for the purposes of these phasors, Q is flowing into the receiving bus. So as long as Q is positive, that's true. But if Q is negative, it's really flowing into the sending bus. Ready for the fun? Look at this. It took me a while to build this model. So what do we got here? It's all in per unit. This red arrow is the receiving voltage. Orange arrow is the sending voltage. Blue phasor is the complex current. The black, again, that's the voltage drop across. And here's our torque angle delta, the difference between VS and VR. So check this out. Look, right now, notice is my current leading or lagging the receiving voltage? Is my current leading or lagging that 0 degree red receiving voltage? Right now it's lagging, right? So notice how if I pull the magnitude of VS back, now the current is leading the receiving voltage. I'm going to pull up a power triangle. So we'll see the difference between the positive and the negative reactive power. So everybody see this? And then notice the change of VX over here. Graphically, KVL, it's right here. Look, VS minus VR is like if we drew an angle from the head of VR to the head of VS. And then when we graph that on the origin, there's V of X. Does everyone see how VX changes, how delta changes, and how the current can change from leading or lagging? What direction does real power always flow? How do we determine that? Sam, that's V of X. That's the same as this. What determines the direction of real power flow? Who remembers? Always from what? Leading to lagging. Great, Patrick. Right now, VS is leading VR. What happens if I drag VS and make it lag VR? Remember, real power and real current, they always flow in the same direction. Um, the current, look, it's helpful to talk about anything to the right of your screen, quadrants 1 and 4, that's a positive current. Anything on the left side of the phasor diagram, quadrants 2 and 3, that's a negative current flowing backwards. Look what happens. When I make VS lag VR, you notice the current is now flowing in the negative direction. Current and real power are now flowing backwards. Why? Real power flows from leading to lagging. Right now, the receiving bus is leading, right? 0 degrees because my sending bus has an angle of about -12. So now the leading bus is the receiving bus, and now the current is negative. Current and real power flowing that way. Pretty cool. All right, let's look at the next one. Now we're looking at just the real component. So this is just like the phasor diagram we drew by hand. So here's VS, complex sending voltage. Here's this vertical black line. That's the imaginary component. I don't really care about that. But here's this black horizontal. That's the real component of VS compared to VR when VR has an angle of 0 degrees as our reference. Who can tell me what's the requirement for the reactive receiving power to be 0? What's the requirement for the reactive receiving power to be 0? Who can tell me in the chat? Great, Alex. Alex said the real component of VS equals VR. Pranav got it too. So look, we can visualize that right about there. See the black arrow and the red arrow are equal? You can't even see them. So if my if my real component of VS is greater than VR, then the reactive power is flowing into the receiving bus because that term in that bracket is going to be positive. Here, that term in that bracket is negative because the real component of VS equals VR. And if I make the magnitude smaller, remember, reactive power is determined by magnitudes, real power is determined by the torque angle. So I've decreased the magnitude of VS, which means I've decreased the real component of VS, and now the real component of VS is smaller than VR. See that? So now let's look at a power triangle. So I'm going to pull this way out here. This red triangle, that's our power triangle. Look at this. Real component of VS, bigger than VR. Is QR going to be positive or negative? When the real component of VS, bigger than VR. QR is going to be positive, right? Q is flowing in this direction into the receiving bus. The receiving bus is acting like a reactive load. So look, here's our power triangle. Look, Q is above the horizontal axis. Look, we've got 0.32 per unit of reactive power. Q is positive. Here's our real power transfer, 0.32. Real power is also positive. So P and Q are flowing into VR. Here's our complex receiving power. Remember, we solved for that first. This is just P, Q, and S, but these are all the receiving variables. Look, got about 0.48 per unit of complex apparent power. Here's our power angle theta, 41.2 degrees. Theta is positive, theta's lagging. What happens if I take VS and I make it lag VR? What's going to change with this triangle? But I'm going to keep the real component bigger than VR. As long as I keep the real component bigger than VR, Q is going to stay positive. Q is going into VR. But if I make VR the leading bus, what's going to happen to P? P is going to go negative. It's going to point in the opposite direction. Let's try that. So I'm keeping the real component of VS bigger than VR, so Q is going to stay up. But as VS gets closer to the horizontal axis, notice, look, P is approaching 0. What condition do I have right here? Do you see P is 0? Who remembers what's the requirement for the real power transfer to equal 0? What's the requirement? Yeah, no delta, said Sam. Delta equals 0. Sine of 0, 0. Here's our delta. I'm pretty close to 0, 0.1, right? These are all rounded numbers here, but 0.1, right? Look, VS and VR, they're like this. They're laying on top of each other. They're exactly in phase. They have the same angle. If they have the same angle, then the same angle minus each other equals 0. Sine of that angle is 0. Real power is 0. All right, let's keep going. I'm going to keep the real component bigger. So look, Q is still positive, right? Q is still 0.33 per unit. Q is still being received into the receiving bus. Now let's make VS lag VR. We're going to make VR the leading bus. What do you notice about the real power? Is the real power positive or negative? Is the real power positive or negative? It's negative. It's on the other side of the x-axis. So in this diagram right here, what direction is P and I flowing in? Is it flowing from VS to VR like it's shown here? Or is it actually showing what? Flowing what? It's flowing backwards. Yeah, opposite, said Lipping. It's flowing from VR to VS. But we still have Q doing what? We still have Q flowing into the receiving bus. Q is positive 0.34 per unit. P is negative 0.19 per unit. All right, let's go back to VS being the leading bus. And what happens to Q as I decrease the VS magnitude so that the real component of VS equals to VR? What's going to happen to Q right here? I'm going to attempt to keep the angle the same. So we're still going to have approximately the same real power. But notice, as the real component approaches VR, yeah, good job, David. Look, Q is approaching 0. The power triangle is falling down onto the 0 axis. So right about there, look, Q is 0. P is 0.3 per unit. Delta is not equal to 0. So P is not equal to 0. We still have some real power. But Q is equal to 0 because the real component is equal to VR. So let's go ahead, let's decrease it. What's going to happen as I make the real component of VS smaller than VR by decreasing the magnitude of VS? What do we expect that power triangle to do? P should still be positive flowing into VR because delta is positive. But what's going to happen as the real component of VS is less than VR? Now Q is negative. P is still positive. P is flowing into VR, right? P is 0.29 per unit, but Q is negative 0.13. Q is being sent out. It's leaving the sending bus. And then one more thing here. Here's all of the variables. Look, you can see how everything interacts, right? Look at that. As Q decreases, if Q is equal to 0, the current and the receiving voltage are going to be in phase because it's a resistive load is what that means. 100% resistive load. So here you can see how everything interacts together. All right, I'm going to go ahead. Looks like great. 100% of you submitted the quiz. I'm going to end that poll, and I'm going to launch the my instructor eval, and then any questions. So we went 30 minutes over. I appreciate everyone that could hang out. I knew this was a little ambitious and trying to get this all done in 1 hour. Hope you guys enjoyed it, though. A lot of fun. I love looking at if we can look at the variables and we understand how we get to the formulas we're using, we're going to understand those formulas much better. We're going to understand what the real proper terms are for those formulas when we're being asked to solve, or if we're trying to calculate these values. It's important to know exactly, right? Receiving and sending, not always the same. What else? Once we get to that, we can see what determines real power, what determines reactive power, what determines the direction of real power, what determines the direction of reactive power, what determines the changes in the quantities. And then my favorite, building these tools, we can really see how all of these values change in real time. Yeah, go ahead and submit my instructor evaluation, please. So we usually do the Q&A at the end. We solved a lot of good questions. For those that can stick around and want to ask some questions, I'm happy to stick around for the next 5 or 10 minutes or so. You know me, I never want to shortchange you. Questions are the best part of learning. If anyone ever shies away from answering your questions, it means they don't really know it well enough to explain it. So always watch out for that. And then before we kind of have some more Q&A in the chat, how did I do? I always like to ask 1 to 5. How much did you enjoy today's seminar? Again, if you stuck around for at least 50 minutes, if you answered all the questions on the previous quiz, I'm automatically going to send you that continuing education certificate, post it on LinkedIn so other people can hear about Ohm Gurus, and then, of course, save it so you can turn it into your state board, get your licensing requirements for free while getting to know each other in the chat. And then long-term too, we're going to have more of a discussion board for Ohm Gurus after the fact on our online community too. So more great fun things to come. I love connecting with you guys in real time, building this community. It's fun. And, we're all real people out there. So it's great to, get to know each other, learn from each other, better each other. Good. I'm seeing all fives. All fives. Great. So this phasor diagram model, I don't have it published yet. I might make it available in the future to play with. We'll see. I'll do my best. It's a fun toy. I got it. There's still some issues with it. Like I don't know why part of the math is breaking out, but that's okay. Yeah, really, really fun toy to play with. You can really see how, look, changing the magnitude while keeping the angle delta the same, all it really changes is the reactive power, but then keeping the magnitude the same and then changing delta is going to change real power, excuse me. Yeah, it's going to change the real power P, but Q will stay the same. So you can see how the delta angle or real power and reactive power, they're independent. What happens if a generator, as more load comes on a generator, how does a utility generator push out power? Power flow and synchronous generator theory, it's extremely similar. It's entirely interwoven, same formulas. If this was a synchronous generator, this would be our internal voltage EO, this would be our synchronous reactance, and that would be our terminal connection E. So these same leading, lagging, overexcited, underexcited relationships, same exact relationships as power flow. It's like looking at the generator as its own bus, generator reactance as the conductor between them, the stator reactance, and then the terminal E as the receiving bus. All right, what do we got? Happy to hang out and chat for those that can stick around. Nicholas says, yeah, if you don't have one, make an article and link to the model. Yeah, I probably will in the future. What I'm going to do is I'm going to cut up this recording into probably 3 or 4 videos. I'm going to post them on our YouTube channel, and then I'm going to post them in our on-demand review course because this is entirely applicable for the PE exam. Joel said it increases its frequency. So when a generator is tied to the grid, it can't change the frequency. The frequency is determined by the overall grid. One generator, it's like a drop in the ocean. So instead, the answer to that question is if a generator is going to make more power, the delta angle is going to increase. More steam on the turbine is going to push the rotor poles further ahead of the stator poles, which is what we call the mechanical torque angle. And then the mechanical torque angle is directly proportional to the electrical torque angle, to delta. So if this was a generator instead of 2 buses, VS would be EO, the internal voltage. VR receiving would just be E, the terminal. A generator pushes more power as delta increases. And in fact, maximum power transfer occurs when your delta angle is exactly 90 degrees. You're gonna get max power. All right, what else? Any other fun questions? Let's see. Sam said, "Is this representative of a transmission line connecting to high voltage?" Yeah, absolutely. That's exactly what this is. That's exactly what this is. Let's see. Anything else I missed? Astro said, "Quick question: the quizzes appear before I hit submit." Sorry, unfortunately, it's a limitation of Zoom. I wish I had a way to do that. Once I end the one poll and launch another, Zoom unfortunately does not let me go back. I'm sorry. All right. Any other questions? What we got? I'm going to scroll up, make sure I didn't miss anything. Yeah, those of you that are asking where to find it, it'll be on our YouTube channel. Let's see, Chris Gibson, are you still here? Chris asked, what's the significance of VX and I being 90 degrees apart? Hey, Chris, good, you're still here. Great observation. That's something we teach about in our PE class when we're talking about synchronous generators. But yeah, let me go back. Let's go back to this one right here, Chris. So yeah, notice, and this is a great question for everyone to look at. Notice as I change VS, what do you notice about the voltage drop VX and the current? The voltage drop is always going to lead the current by 90 degrees. That's a perfect right triangle. And this gray arrow, that's VX, right? That's KVL. VX equals VS minus VR. That's like drawing a phasor from the head of VR to the head of VS. And then we take that gray arrow and we just plot it on the origin. It's just a different way to show that graphically. But yeah, notice it's always leading I by 90 degrees. Who knows? Who can answer in the chat? Who took the PE class? Who took the PE class? Let's see. Jay said Nicholas. Yeah. It's because of the reactance, says Alex. Yep. So Chris, you asked that, right? I'm trying to find you in the chat. There you are. Hey, Chris. So yeah, so look, so we've got J of X. What's the voltage drop equal? Ohm's law, V equals I times Z. V of X equals this current I times Z, which is J of X. So in polar, I times J of X, we multiply their magnitudes. In other words, this magnitude 0.3, let me see if I can get my calculator. I don't know if I can no, I can't. It won't let me superimpose it on the full screen. But if you get your calculator, look, magnitude I 0.41 times, I don't remember what I used to model this reactance. I think it might have been like 8% maybe. But anyways, 0.3 magnitude Vx, that's equal to the magnitude of X times I. And then when we multiply two polar numbers, what do we do to the angles? We add the angles, we sum them up. So whatever the angle is of I, if we add it to J, if we add it to 90 degrees, we're going to get the angle of V of X. Angle of I right here is negative 19.3. Negative 19.3 theta I plus J theta Z 90 degrees is 70.7 degrees. This right angle between Vx and I, that's the J operator. That's your 90 degree J operator because there's no resistance. So the angle of this impedance is going to be 90 degrees because this impedance is J times X. So yeah, that right angle that you spotted right away, Chris, that's your J operator. That's I times J of X equals V of X. What else? Ahmed said, why are we multiplying Vs magnitude by the cosine of delta to get the real magnitude of Vs? Well, we should multiply by cosine theta angle. Okay. So Ahmed is asking, right here, Ahmed is asking, to get the real component of Vs, why are you doing magnitude Vs cosine delta? Why not magnitude Vs cosine theta S? Great question. So Ahmed, typically when we model this, we use a reference of 0 degrees for VR, right? We put VR right on the horizontal. Since delta is this angle minus this angle, remember, phasors, they're flying around 60 times a second for a 60 hertz system. So a phasor diagram, you're looking at a snapshot in time. It's like if you took a camera and went right on the phasor diagram, you stopped it. So these relationships, they're all rotating, but they're all the same. They're all going to be the same distance apart, all that good stuff. So we're going to say we want to look at it when VR equals 0 degrees. It's way easier to analyze. We know right away which one's leading, which one's lagging. It's just way simpler on the math. So since delta is Vs minus VR, when we use an angle of 0 for VR, delta equals theta Vs minus 0. In other words, if the phasors were like this, what we're saying is we're going to rotate Vs and VR until VR is perfectly flat on the horizontal. I'm pointing this way. On my screen, it's the same size, maybe same way. Maybe I got to point like this. Does that match the same direction as the phasors on your screen? For me, it looks backwards, but I'm looking at it. So in other words, like we're saying, hey, we're going to rotate Vs and VR until VR is exactly on the horizontal. And that's it for our final video in Power Flow and Power Transfer Continuing Education Seminar for Professional Engineers by Ohm Gurus. If you're an electrical engineer and you're ready to pass the PE exam, you can learn more about our online class by visiting www.electricalpereview.com. Or if you're already a licensed engineer and you're looking to gain new skills while earning continuing education certificates for licensing renewal, you can join seminars just like this one, both live and on demand, hosted by myself and other licensed engineer guest speakers by visiting www.ohmgurus.com. Links to both are in the description at the bottom of this video.